Tonight, we're going to explore a machine that isn't really a spaceship at all. Because this vessel isn't just meant to carry people from one place to another. It's meant to do something far bigger. It has to become everything our planet currently does for us, all at once, forever, with no room for failure. Air, water, food, gravity. A magnetic field, strong enough to hold back radiation that would otherwise tear through every cell in the human body. And it has to keep doing all of it, without failure, for centuries, with no planet nearby to fall back on if something breaks. By the end of tonight, you're going to understand exactly what it would take to build a ship like this, and why replicating an entire planet might be harder than reaching the stars themselves. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Now, let's begin. The reason we're even having this conversation is simple. Earth has an expiration date, not tomorrow or next century. But the Sun is not a permanent fixture. It's a middle-aged star, about 4.5 billion years into a roughly 10 billion year life cycle. And as it ages, it's getting brighter, about 10% brighter every billion years. In approximately 1 billion years, that extra heat will be enough to push Earth's average surface temperature past the point where liquid water can persist at the surface. The oceans begin to evaporate. The water vapor drifts into the upper atmosphere, gets broken apart by ultraviolet radiation, and the hydrogen bleeds off into space. Earth doesn't freeze. It dries out. It bakes. And long before that billion-year mark, conditions will have become difficult enough that what we recognize as Earth will be gone. That's the slow version. There are faster ones. A large enough asteroid impact at the wrong moment. A supervolcano eruption that buries the northern hemisphere in ash and plunges global temperatures by several degrees for years. A nuclear exchange that does something similar. A pathogen we weren't ready for. A climate system that tips past a threshold we can't come back from. None of these are guaranteed, but none of them are ruled out either. And the uncomfortable truth is that a species living on a single planet is placing all of civilization on one geological roll of the dice. There's a direct line between that reality and the idea we're exploring tonight. Spreading to other worlds isn't a luxury. From the standpoint of long-term survival, it's the only rational move. The problem is the distance. The nearest star to our Sun is Proxima Centauri. It sits about 4.24 light-years away. A light-year is the distance light covers in a single year, moving at roughly 670 million miles per hour. 4.24 light-years is approximately 25 trillion miles. Our fastest spacecraft, the Voyager probes launched in 1977, are moving at roughly 38,000 miles per hour. At that speed, reaching Proxima Centauri would take about 75,000 years. Nobody is waiting 75,000 years to get anywhere. So we need to go faster. The question is, how much faster, and what the cost of that speed actually is. If we could reach 1% of the speed of light, roughly 6.7 million miles per hour, the trip to Proxima Centauri would take about 420 years. 2% gets you there in about 210 years. 5% puts it at roughly 85 years. 10%, which would require more energy than anything humanity has ever produced, gets you to about 42 years. No existing engine can do any of this. There's a concept worth understanding here called specific impulse. It's the measure of how efficiently a rocket uses its propellant. A higher specific impulse means more thrust per unit of fuel. Chemical rockets have a specific impulse of around 450 seconds. That sounds technical, but what it means in practice is that for every kilogram of fuel you burn, you get a certain amount of velocity. Nuclear thermal propulsion gets you to around 900 seconds. Ion drives, which fire charged particles at very high velocities, can reach specific impulses of 3,000 to 10,000 seconds. But even ion drives produce tiny amounts of thrust. They're efficient but slow to accelerate. A generation ship using ion propulsion would take decades just to reach cruising speed. That's acceptable in theory. The journey is centuries long anyway. A few extra decades at the beginning barely registers against the overall timeline. The problem is the fuel mass. Even with the most efficient drives we can realistically envision, the mass of propellant required to push a city-sized ship to 1% of light speed dwarfs the mass of the ship itself by enormous margins. This is the rocket equation at work. It was derived by Konstantin Tsiolkovsky in 1903, and it has been the fundamental constraint on rocketry ever since. The equation tells you that to achieve a given velocity change, you need a certain ratio of propellant mass to final mass. The higher the velocity you want, the exponentially larger that ratio becomes. Getting to 1% of light speed requires a propellant-to-payload ratio that is, for any conventional propulsion system, essentially impossible to achieve in one step. You'd have to stage the propulsion, launch the ship in pieces, accelerate it over many years using a series of propulsion systems, some of which might be external. A laser sail pushed by an enormous laser array back in the solar system. A magnetic sail that extracts momentum from the solar wind during the early part of the journey. Multiple stages of onboard propulsion that burn sequentially as fuel is exhausted and empty tanks are jettisoned. None of this is clean. All of it adds complexity. But it might be the only way to get the mass fractions to work. The most energetic propulsion system we've seriously tested is nuclear thermal, which roughly doubles the efficiency of a chemical rocket. That's nowhere near enough. To reach even 1% of light speed, you'd need propulsion based on principles we haven't yet demonstrated at scale. Fusion engines, antimatter drives, solar sails pushed by enormous laser arrays fired from within our solar system. All of these are theoretically grounded. None of them exist as operational hardware, but the physics doesn't prohibit any of them. And for the purposes of thinking through what a generation ship actually requires, we don't need to solve propulsion first. We need to understand something more fundamental. What does it mean to keep human civilization alive, functional, and coherent across a journey measured in centuries? That's the question that keeps engineers awake. Picture the ship, not the sleek dart of science fiction. Something more like a rotating cylinder, or a torus, a giant ring spinning around a central axis. The rotation is deliberate. Spin a cylinder fast enough, and the people inside experience centrifugal force pressing them toward the outer wall. At the right rotation rate, that force mimics gravity. Without it, you're dealing with the full consequences of long-term weightlessness. Bone density loss, muscle atrophy, cardiovascular changes, vision problems caused by fluid shifting toward the head. These effects begin within weeks, in microgravity, and compound over years. A population that has lived in zero gravity for 200 years would arrive at another star system in a state of significant physiological decline. So, you rotate the ship. A cylinder, roughly 1 mile in diameter, spinning about 1 rotation per minute, produces approximately 1 gravity at the outer wall. That's the engineering baseline. The structure itself has to be miles in length to provide enough interior volume for a viable population, for agriculture, for industrial functions, for everything a small civilization needs to maintain itself. We're talking about a structure with the mass of a large bridge, or several large bridges, that has to survive a journey measured in centuries without any external maintenance. Every weld, every seal, every bearing, every circuit has to either last for the duration, be replaceable with onboard materials, or be backed up by something redundant that can take over when the primary fails. Materials degrade. Metal fatigues under cyclic stress. Seals crack. Radiation erodes electronics. Whatever you build today, in 100 years its performance is degraded, and in 300 years it is a different object than the one you made. This is not a construction problem. It's a civilization problem. The ship has to contain within itself the knowledge, the tools, and the human capacity to maintain and repair itself indefinitely. Not just for the first generation, who were trained on Earth by experts. For every generation that follows. The 10th, the 30th. The generation that won't be born for 200 years and will inherit this machine from people they've never met, knowing they're responsible for keeping it running for people they'll never meet either. There's a concept in engineering called a single point of failure. It's a component or system whose failure causes the entire larger system to stop working. Good engineering eliminates single points of failure through redundancy. You back up critical components with duplicates or alternates that can take over if the primary fails. On a generation ship, you need this applied at every level. Not just the engines, not just the life support, but the knowledge to operate and repair both. If the only person aboard who understands how the water recycling chemistry works is removed from the picture, and the system develops an unusual problem, and the documentation isn't clear enough for someone without that background to diagnose it, then the loss of one person becomes the beginning of a cascading failure. This is why redundancy in a generation ship is not a feature. It's the entire architecture. Every critical skill needs multiple people trained in it. Every critical system needs multiple backups. Every critical piece of knowledge needs to exist in multiple formats, written, demonstrated, tested regularly, embedded in the training curriculum so it passes to the next generation intact. This is harder than it sounds. It's hard to maintain training standards for procedures that have never had to be used. Humans are not naturally good at preparing for rare events. We tend to prioritize the immediate over the distant, the routine over the contingency. A ship culture that genuinely maintains readiness for unlikely failure scenarios, consistently, across generations, is a culture that has solved a problem that most human organizations struggle with, even on Earth. The ship has to grow its own food. There's no other option. You cannot carry enough calories for thousands of people across a journey that lasts centuries. The mass alone would be prohibitive. What you can carry is seeds, biological cultures, and the infrastructure to produce food continuously from basic inputs. Hydroponics. Closed-loop agriculture, where plants grow in trays under artificial light, their roots bathed in nutrient-rich water that gets recirculated and replenished. The plants produce oxygen as they grow. The crew exhales carbon dioxide, which the plants absorb. Organic waste gets composted and fed back into the growing cycle. Water is captured, filtered, and reused indefinitely. Nothing leaves the system. Every molecule that entered when the ship launched has to still be there when it arrives. This is called a closed-loop life support system, and it's one of the most complex engineering challenges in this entire picture. On Earth, the biosphere manages this automatically. It's been evolving to do it for billions of years. The oceans buffer the carbon cycle. The soil microbiome breaks down organic material. The atmospheric chemistry maintains oxygen and nitrogen in proportions compatible with life. All of this happens without human management. On a generation ship, humans have to replicate the relevant parts of that system in a structure that weighs only a fraction of Earth's biosphere, at a fraction of the energy budget, with zero tolerance for failure. You'd grow grains, legumes, vegetables. You'd probably have some protein from cultured meat or insects, which are extraordinarily efficient converters of plant material into protein. An insect converts roughly 2 kilograms of plant material into 1 kilogram of protein, compared to roughly 8 kilograms of plant material for 1 kilogram of beef. On a generation ship, that ratio matters. Every kilogram of food you produce more efficiently is a kilogram you don't have to grow, which is space and energy you can use for something else. The diet on board will not look like the diet of a prosperous Earth city. It will be nutritionally complete. It may occasionally be monotonous, and the people eating it will adapt to it, as humans have always adapted to the food their environment provides. The agricultural system isn't just about calories. It's about atmosphere management. Every plant that grows is performing photosynthesis, consuming carbon dioxide and releasing oxygen. Get the balance wrong, and the atmosphere inside the ship shifts in ways that are slow but serious. Too much carbon dioxide and cognitive function degrades. People become sluggish, make more errors, feel persistent headaches. Not immediately dangerous. But over weeks and months, as the balance drifts further, the consequences compound. You need the agricultural area sized precisely to the population it supports. Not just for food production, for atmosphere management, for carbon dioxide scrubbing, for humidity control. The plants are not just the kitchen, they're part of the life support. And if a significant portion of the growing area fails, the problem is not just hunger. It's atmospheric degradation happening simultaneously. The energy to run all of this has to come from somewhere. A nuclear fission reactor is the most realistic near-term option. A large one, or several, running in parallel. Fission reactors can run for decades on a fuel load, but decades is not centuries. You'd need to carry enough fuel for the entire journey, or you'd need the ability to reprocess spent fuel on board, extracting fissile material from the waste and using it again. This is called closed-cycle fuel reprocessing, and it exists in limited forms on Earth. Doing it reliably aboard a spacecraft for centuries is another matter. Fusion reactors, if we ever develop them to operational reliability, would be significantly better. The fuel is hydrogen, which is the most abundant element in the universe. A fusion reactor, burning hydrogen, doesn't produce the long-lived radioactive waste that fission does. The maintenance burden is different. The fuel situation is better. The energy output for a given fuel mass is orders of magnitude higher than fission. We don't have operational fusion reactors yet. The physics works. The engineering remains unsolved after 7 decades of serious effort. But the trajectory of progress suggests that reliable fusion power is a question of when rather than whether. And the when might be within this century. A generation ship launched 100 years from now might launch with fusion reactors as a baseline assumption rather than an optimistic hope. For now, the working assumption is that you carry what you need, which means the ship's mass at launch is dominated by fuel. Most of what you're accelerating is the stuff that's doing the accelerating. This is the tyranny of the rocket equation. The more mass you need to move, the more fuel you need. The more fuel you carry, the more mass you have. The more mass you have, the more fuel you need to move that. It compounds in a way that makes the numbers very large very quickly. A ship capable of reaching 1% of light speed, carrying 10,000 people and everything they need for 400 years, would require a launch mass so enormous it strains any realistic estimate of what humanity could build at our current level of development. Some proposals suggest that the ship wouldn't launch from Earth at all. It would be built in space, assembled at a construction facility in orbit, fueled by material mined from asteroids or the outer planets. That's a massive infrastructure project in its own right. You're building a civilization in space before you even launch the ship. But that's actually how it would have to work. You don't bootstrap interstellar travel from the surface of a planet. You build the capacity for it incrementally, over decades or centuries, until the ship becomes possible. The generation ship is not the first step. It's the product of 100 previous steps, each one hard, each one necessary. The question of how many people need to be on the ship is not a guess. It's a calculation. Population genetics gives you hard limits. If a population is too small, genetic diversity declines. Related individuals breed with each other by necessity. Harmful recessive mutations, which are normally suppressed because you need 2 copies to express them, start showing up more frequently because everyone shares common ancestors. This is called inbreeding depression. It's been documented in island populations, in captive animal breeding programs, in historical cases where isolated human communities became genetically bottlenecked. The consequences are real, and they compound across generations. Higher rates of genetic disorders, reduced immune system diversity, lower fertility, shorter average lifespans. The minimum viable population to avoid this on a multi-century voyage has been modeled by researchers including Cameron Smith at Portland State University. His analysis, published around 2014, concluded that you need a founding population of at least 10,000 people to maintain adequate genetic diversity across a journey of 200 years or more, even accounting for reasonable birth rates and some degree of attrition. Earlier estimates, which floated around 500 to 1,000 people, were based on models that didn't fully account for genetic drift, the random variation in which genes get passed to the next generation in a small population. When you model drift realistically, the required founding population goes up substantially. 10,000 people. That's not a crew. That's a small city. And that city has to fit inside a structure that can cross interstellar space. The math gets harder from there. 10,000 people need roughly 2,000 calories per person per day. That's 20 million calories per day. Over 400 years, that's roughly 3 trillion calories. Growing that much food requires significant agricultural area. Estimates for closed-loop hydroponic systems designed for human nutrition tend to run around 30 to 40 square meters of growing area per person. For 10,000 people, that's 300,000 to 400,000 square meters of growing area. All of it inside the ship. All of it lit artificially. All of it continuously managed. And the ship has to be spinning to generate artificial gravity, which means the agricultural area is on the inner surface of a rotating structure, which introduces design complications that don't exist in a conventional building. The Coriolis effect, the deflection caused by rotation, affects how water flows through the growing systems, affects how pests and pathogens spread through the growing area, affects the optimal orientation of plant trays. The physics of a rotating habitat is not the same as the physics of a terrestrial environment, and every system designed for one has to be redesigned for the other. This is why generation ships are hard. It's not one engineering problem. It's every engineering problem, all at once, for centuries. The people who board the ship make a choice. They volunteer. They understand, at least intellectually, that they will spend their entire lives on this vessel and never see a destination. Their contribution is the journey, not the arrival. That's a specific kind of person, and it's worth thinking about what motivates them. You'd be leaving behind everything. Every person not on the manifest. Every landscape you've ever seen. Every city. Every smell that belongs to Earth. The sound of wind through actual trees. Rain on actual soil. You'd be trading all of that for a metal cylinder moving through a darkness where the nearest help is measured in decades of travel time. The people who sign up for this know that. They sign up anyway. Some will do it because they believe in the mission, in the necessity of carrying humanity beyond this solar system. Some will do it for the history of it, to be the founding generation of something that has never been done. Some will do it because they have nothing holding them here, or because what's holding them here isn't enough to outweigh what's pulling them there. The selection process for these people would be extraordinarily demanding. You'd want the obvious things. Technical expertise across every relevant discipline. Physical health robust enough to sustain across a long life in a controlled environment. Psychological stability under extreme conditions. The ability to function in close quarters with the same group of people for decades. But you'd also need something harder to measure. The capacity to find meaning in constraints. The willingness to subordinate personal preferences to collective needs, not occasionally, but consistently, over a lifetime. The ability to transmit values to children without becoming authoritarian about it. The resilience to face genuine grief and keep functioning. The understanding that most of the things that make Earth feel like home, the specific things, the way the light falls in a particular park, the smell of a particular coast, the sound of a particular language spoken by strangers in a street, none of those are coming with you. And being at peace with that, not in the resigned way, in the genuine way. These traits exist. Some people have them. The selection process would be finding them. And then there will be children born on the ship. Not the first generation. Not even the second. But every generation after, these people made no choice at all. They were born into a world that consists entirely of corridors and growing bays and recycled air, into a community that knows nothing else and cannot leave. Every ethical question about generation ships eventually arrives here. You are not just asking a group of volunteers to commit to a dangerous journey. You are committing their descendants, who don't exist yet and cannot consent to that same journey, to that same constraint for their entire lives. This has no clean answer. It never has. Humans have always made decisions that bind their children. Where you're born, what language surrounds you, what culture shapes you, what resources you inherit or don't. A generation ship takes this to its logical extreme. The children will be shaped by a vessel, by a mission, by a destination none of them will ever see. You can call that an imposition. You can also call it the condition of being human. Every one of us was born into a world we didn't choose. The ship is just a more concentrated version of that. Now think about how that ship is governed. The first generation has a clear structure. They came from Earth. They were selected by some combination of expertise, physical fitness, and psychological stability. They have a chain of command, a mission protocol, a set of rules designed by the people who built the ship and planned the voyage. They believe in what they're doing. They have a living memory of why. The second generation inherits all of this. They've grown up watching their parents live inside the structure. They understand it from the inside, but they didn't design it. And some of them will start to wonder whether the rules make sense, whether the hierarchy is fair, whether the mission is worth the cost they're being asked to pay. The fifth generation has grandparents who were born on the ship. Earth is not a memory. It's a story. Something from the archive, from the recordings, from the oral tradition that the original crew tried to preserve. The fifth generation knows what Earth looked like. They've seen the footage. They just don't feel it the way the founders did. The 20th generation lives inside a culture that has been evolving for 4 centuries. The language has drifted. The traditions have been modified and adapted. New rituals have emerged that the founders would not recognize. The mission is an ancestral obligation, not a personal one. These people didn't volunteer. Their great-great-great-grandparents did. The question of whether they still have to go where those ancestors pointed the ship is not trivial. In history, this has happened at smaller scales. Families displaced by circumstances beyond their control, communities bound by promises made generations before any of the living members were born. What we know is that people are not loyal to abstractions. They're loyal to each other, to the people they know, to the community they live inside. If the mission becomes an abstraction, loyalty to it weakens. And if loyalty to the mission weakens enough, something changes on board. Maybe it's gradual. Maybe it's a slow drift in priorities. Maybe it's faster. A leadership transition that doesn't go smoothly. A faction that decides the destination doesn't matter as much as the conditions of life right now, on this ship, among these people. A vote that nobody on Earth would have any standing to override. Because Earth is 300 years away, and the ship is here. This is mission drift, and there is no obvious engineering solution to it. You can write it into the founding documents. You can build monuments to the original purpose. You can tell the story in schools, embed it in ritual, make it part of what it means to be a member of this community. But you cannot guarantee that people 200 years from now will feel what the founders felt when they looked at the stars and decided to go. What you can do is design the social architecture carefully from the start. The governance structure matters enormously. If you establish a rigid hierarchy, a command structure like a naval vessel, you get efficiency and coherence in the short term. You also get brittleness. Rigid systems break when conditions change in ways the original designers didn't anticipate. And conditions will change. They always do. If you establish something more democratic, a council-based system, a representative structure, you get adaptability. You also get politics. Competing factions. Elections that change the direction of policy. Leaders who win by promising things that are popular in the short term, even if they're harmful in the long term. There is no governance model that is immune to human nature. The most realistic assessment is that the government of a generation ship, whatever form it takes at launch, will look different 100 years later. Significantly different 200 years later. And there's no way to know in advance whether those differences will be improvements or disasters. What you can do is build institutions that are hard to destroy even when individuals want to destroy them. Distributed authority. Multiple overlapping systems of accountability. A culture that values the mission enough to resist anyone who would abandon it. But culture is a living thing. It can't be frozen. You build a culture, and then it grows, and after enough time, it's something you didn't build, something that grew from what you built. And you won't be there to see what it became. There's a concept from social psychology called in-group and out-group dynamics. Humans are tribal by nature. We form strong attachments to the groups we belong to, and we define ourselves partly in opposition to groups we don't belong to. On Earth, this tendency produces both the warmth of community and the ugliness of prejudice. On a generation ship, it produces something more complicated. In the early generations, the in-group is clear. We are the people on this ship. Earth people are the out-group, increasingly distant, increasingly abstract. But within the ship, new distinctions will form. The people who work in the agricultural section versus the people who work in engineering. The families from certain original cultural backgrounds versus others. The people who support the current governance structure versus those who oppose it. The technically trained versus those whose work is more social or creative. These distinctions will solidify into something like social classes. Not necessarily rigid ones, not necessarily unjust ones, at least not initially. But the hierarchy of who matters more, whose skills are more valued, whose section of the ship is more comfortable, will emerge. It always does. History shows no example of a complex human society that didn't develop social stratification of some kind. The question is whether the stratification is manageable. Whether it remains permeable enough that people can move between levels through effort and talent. Whether the lower rungs of the social hierarchy have enough dignity and enough resources that they remain part of the community rather than becoming an alienated underclass. An alienated underclass on a generation ship is not a social problem you can contain. It's a structural threat. People who feel that the system is designed against them, that their contributions are undervalued, that their children will face the same constraints they did, are people who eventually stop maintaining that system, or worse. Managing inequality on a generation ship is not a soft problem. It's as critical as managing the water supply. The question of expertise versus democracy runs through all of this. Running a generation ship requires technical knowledge, the kind that takes years to acquire and can't be replaced by good intentions. If your water recycling system is failing, you need someone who understands water recycling chemistry, not someone who was elected on a platform of water recycling reform. The person who understands the system. There's a real tension between the democratic impulse, giving people a voice in the decisions that affect their lives, and the technical requirement, putting decisions in the hands of people who are actually qualified to make them. This tension exists on Earth too. We navigate it imperfectly. On a generation ship, the consequences of navigating it wrong are more immediate. Electing a leader who ignores the engineers when the engineers say the reactor needs maintenance doesn't produce a policy dispute. It produces a dead reactor. And a dead reactor, on a ship in interstellar space, is a different category of problem than it would be in a power plant on Earth. The architecture that threads this needle probably involves tiered authority, technical decisions within defined domains made by people with demonstrated expertise in those domains. Strategic decisions about mission priorities, resource allocation at the macro level, social policy, made by a broader representative process. The two systems need to be designed so they can't undermine each other, so that no elected official can override a technical expert on a matter of engineering, and no technical expert can make social policy without democratic accountability. This sounds clean in theory. In practice, the boundaries blur. The reactor engineer and the council chair are both people, with relationships, with histories, with interests. The line between technical judgment and political judgment is never as clean as the org chart suggests. Let's go inside the ship, not to the command deck, down to where most of the people live. The living quarters are not generous. You need space for tens of thousands of people inside a structure that has to be accelerated across interstellar distances. Every square foot of habitable space is a square foot that has to be heated, pressurized, cleaned, maintained, and protected from radiation. Think of it less like a luxury cruise liner and more like a very well-designed apartment building that happens to be moving at several % of light speed. People have private quarters. Small. Enough for a bed, a desk, storage, a personal space that belongs to you. The communal areas are where life happens. Shared dining, shared recreation, public gardens where the growing systems are partly ornamental, partly agricultural. Corridors that curve upward when you follow them long enough because you're on the inside of a cylinder. Windows that look inward, across the habitat, not outward into space. The view outside is not calming. Interstellar space is not the starfield of science fiction. At 1% of light speed, after a month of travel, the stars have barely shifted. After a year, slightly more. After 100 years, you've crossed a distance that takes light years to reach. And the stars still look roughly the same. The universe is simply that large. There is no visual sense of progress. No coastline getting bigger as you approach. Nothing to tell you that you're moving, except the instruments. And the instruments say, 400 years to destination. Then, 397. Then, 394. This is the environment in which 20, 30, 40 generations will live and raise children and grow old. The psychological architecture of this has to be as carefully engineered as the structural one. You need work that is meaningful. Not make work, not busy work, but actual roles that actually matter to the survival of the ship. When the water recycling system develops a problem, someone has to fix it. When the crop yields in growing Bay 7 drop below the baseline, someone has to figure out why. When a child is sick and the medical system flags an anomaly, someone has to diagnose it. Purpose is not optional. A population without purpose is a population in slow disintegration. You also need space for things that have no immediate practical value. Art, music, games, philosophy, sports, probably. Whatever the on-board equivalent of sports looks like in a rotating cylinder, where the physics is slightly strange, where balls curve in unexpected directions as the Coriolis effect acts on them, where the rules of athletic competition had to be reinvented for an environment no sports designer in history ever anticipated. These things are not extras. They are part of what makes a community function across generations. Every culture in human history has them. The ones that tried to suppress them didn't last. The generation ship cannot afford to suppress them. It cannot afford to suppress much, actually. There's a recurring temptation in thinking about enclosed, high-stakes environments to imagine that strict control is what keeps everyone safe. That's partially true. There are things that genuinely require tight regulation on a generation ship. Reproduction rates, resource consumption, access to critical systems. You cannot let population grow faster than the ship's agricultural capacity can sustain. You cannot let any individual consume more than their allocated share of water or power without consequences. You cannot leave critical systems unguarded. These constraints are real and non-negotiable. But the impulse to extend control beyond what's necessary, to regulate behavior that doesn't threaten the ship's survival, to create a rigid hierarchy that concentrates power in a small leadership class, that impulse is its own threat. History does not have good examples of isolated, enclosed communities that thrived under authoritarian control over long periods. It has examples of them becoming oppressive, brittle, and eventually explosive. The generation ship that launches with a sensible governance structure has no guarantee that structure will hold. But the one that launches with a rigid, top-down hierarchy almost certainly won't survive intact for 1,000 years. The question of reproduction is one where this tension is most acute. You need people to have children, enough to replace the people who are gone and maintain a stable population, but not so many that you exceed the ship's capacity to feed and house them. You need to hit a narrow target. Enough births to replace losses. Not so many that you exceed carrying capacity. And you need to maintain this balance for centuries. Any persistent deviation accumulates over time. A small decline in birth rate, just a few percentage points, compounds over generations. A small increase leads to resource strain that also compounds. How do you regulate this without crossing into territory that most people find deeply objectionable? Some proposals suggest a lottery system for birth permits. Each year, a number of permits are made available, proportional to the population loss of the previous year. Couples who want children enter the lottery. Winners get permission to conceive. Losers wait and try again. It's random, which feels fairer than alternative approaches. But randomness means some people who desperately want children might wait years before winning, while others who are ambivalent might win on the first try. Other proposals suggest merit-based selection, where couples are evaluated on their genetic health, psychological stability, and demonstrated ability to parent. This is more efficient from a population health standpoint. It's also deeply uncomfortable. You are now making an official judgment about whether a specific person is worthy of having a child. The history of policies like that on Earth is not encouraging. There are no good answers here. Every option involves an uncomfortable trade-off between individual reproductive freedom and collective survival. The ship's designers will have to choose something, and whatever they choose will shape the culture of every generation that follows. One of the challenges nobody likes to talk about is what happens when things go wrong at a biological level. Not mechanical failure, genetic failure. A founding population of 10,000 people sounds like a lot. But genetic diversity doesn't scale linearly with population size. It scales with effective population size, which accounts for which individuals actually contribute offspring to the next generation. If the founding population is 10,000, but only half of them reproduce, and within that half, there are patterns, certain families producing more children than others, certain genotypes turning out to be slightly more fertile or slightly more attractive as mates, the effective population size drops. It might drop significantly. And over generations, even small biases in who reproduces compound. Certain genes become more common. Others drift toward rarity. Some disappear entirely. This is called genetic drift, and it happens in every small population, including ones that seem large enough to be immune to it. The consequences play out slowly. After 100 years, the population looks fine. After 300 years, certain inherited conditions are appearing at slightly higher frequencies than they did at launch. After 600 years, the pattern is undeniable. The genetic health of the population has quietly degraded while everyone was focused on keeping the engines running and the crops growing. There are ways to counter this. You can freeze embryos or gametes at launch, preserving genetic diversity from the founding generation in a form that doesn't consume resources or require housing. Periodically, over the course of the journey, the ship can use those frozen samples to introduce genetic diversity that would otherwise have been lost. Effectively, the founding generation donates genetic material to future generations they'll never meet. It's a strange kind of legacy, but it works, in principle. The technology to do this is not speculative. We can freeze human reproductive cells and embryos today and thaw them decades later with high success rates. A generation ship would need this capacity from launch, maintained continuously, and used strategically across the journey. The other option is genetic engineering. As technology improves, the ability to identify and correct harmful mutations in embryos improves with it. A generation ship, 100 years into its journey, might have the technical capability to screen every embryo conceived on board and correct known genetic problems before implantation. This raises questions about who decides what counts as a problem, what counts as a mutation worth correcting versus a variation worth preserving. These are not hypothetical, ethical dilemmas. They are the kind of real disagreements that fracture communities. You can imagine, quite easily, a society on board that has divided over this exact question. One faction that sees genetic management as essential to the mission's survival. Another that sees it as an overreach, an intrusion into the most intimate decision a person can make. Both positions are comprehensible. Neither is wrong in any simple sense. And the ship has to function with both groups on it. For centuries. That's the social landscape inside the vessel. Not a unified community moving toward a shared goal. A complicated, living, disagreeing society that happens to also be a spacecraft. Radiation is a constant companion. Earth's surface is shielded by the planet's magnetic field and by the atmosphere. These two things together reduce the cosmic ray flux at ground level to a small fraction of what exists in open space. On the generation ship, you have neither. You have shielding. Thick layers of water or polyethylene or some combination of materials that absorb incoming particles before they reach the crew. But shielding has limits. The highest energy cosmic rays, the ones produced by supernovae and active galactic nuclei, can punch through almost anything. Not in large numbers. But consistently, over decades, delivering a slow, accumulated dose to everyone on board. Over a lifetime, this raises cancer risk. Over a generational span, it introduces mutations into the gene pool. Over centuries, the cumulative effect is measurable in population health outcomes. There's no solution to this that doesn't involve mass. More shielding means more mass. More mass means more energy to move. There's a point where the shielding is heavy enough to be self-defeating. What you actually do is build enough shielding to bring the dose down to an acceptable level. And then you accept the residual risk. You track it. You manage the medical consequences as they arise. You accept that the population on board will, on average, face a slightly higher lifetime cancer risk than a population living on Earth. This is one of many ways in which life on the generation ship is simply harder than life on a planet. It's not catastrophically harder, not in any single dimension. But the hardness accumulates. Radiation risk, limited space, constrained diet, no experience of weather, of seasons, of the natural world that shaped human psychology over hundreds of thousands of years. The sky is a ceiling. The horizon is a wall. The darkness outside the hull is not like the darkness of a rural night. It's absolute, empty, and it goes nowhere that the living will ever reach. What that does to people across generations is something we genuinely don't know. We have studies of long-duration, isolation, polar expeditions, submarine crews, space station inhabitants. The longest any human has spent continuously in space is just over 14 months. That data is useful, but it doesn't extend to the conditions of a generation ship where the isolation is permanent and the population includes children who have never known anything else. The psychological architecture of the ship has to be designed to counter this in ways we're still working out. Meaningful work is part of it. Community connection is part of it. Access to simulated natural environments, virtual spaces that give the brain the sensory input it evolved to process, is part of it. Some proposals suggest that the interior of the ship should be designed to mimic a natural landscape as closely as possible. Not just functional growing bays, but actual parks, with soil and trees and simulated sky, where children can play in something that feels like the outdoors, even though it isn't. The simulated sky is worth a moment. The human brain is calibrated to a 24-hour light cycle. It has been for as long as the species has existed. The relationship between daylight, hormone production, sleep quality, mood, and long-term mental health is well documented. Disrupting that cycle has real consequences, as anyone who has worked rotating shifts or crossed multiple time zones can tell you. A generation ship with no sun needs to simulate it. Full spectrum lighting that rises and sets on a schedule. Not just bright versus dark, but the shifting color temperature of morning light, transitioning to the blue-white of midday, transitioning to the warmer tones of afternoon. This may sound like a design detail. It is actually a physiological requirement. The people inside the ship need to feel a day. They need to feel a season, even an artificial one. The circadian rhythm is not an optional feature of human biology. It's embedded in the body's chemistry at the cellular level. Ignore it, and you degrade the health of every person on board. Maintain it, and you've done something important for the long-term functioning of your civilization. The scenario that ends everything is not always dramatic. Sometimes it's a small failure that cascades. The water recycling system develops a blockage. The maintenance team patches it, but the patch isn't quite right. Over 6 months, the efficiency of the system drops by 12%. The drop is small enough that it doesn't trigger alarms immediately. But 12% of the water that should be recovered is instead being lost. 12% becomes 20% as the imperfect patch degrades. By the time someone notices the trend in the data, the reserves have dropped. Not to crisis levels. Not yet. But the margin is gone. And now there's a failure in a different system. The agricultural lights in Growing Bay 3 develop a power fluctuation. The crops there get inconsistent light. Yields drop. Food production falls by 8%. Add that to the water deficit and you have a compounding shortfall. Not a catastrophe in a single moment. A slow squeeze. A narrowing of the margin between what the ship produces and what the population needs. Leadership begins rationing. Rationing creates conflict. Conflict diverts attention from maintenance. More systems degrade. The spiral tightens. This is the failure mode that doesn't show up in the simulations because it's not a single dramatic event. It's the accumulation of small problems, each manageable on its own, that interact in ways nobody predicted. The generation ship has to be designed with enough redundancy that no single failure can start this chain. And it has to have a governance structure capable of catching slow trends before they become crises. Both of those requirements are harder than they sound. Redundancy is expensive. Every backup system is mass. You're accelerating across interstellar space. And governance that can catch slow trends requires leadership that is willing to deliver bad news. An institutional culture that rewards early warning rather than punishing the people who raise concerns. These things are not guaranteed. In the history of complex human organizations, they are actually quite rare. Organizations tend toward denial. They tend to punish messengers. They tend to prioritize short-term stability over long-term accuracy. On Earth, these tendencies cause failures that are recoverable. On a generation ship, 300 years from the nearest help, the same tendencies could be fatal. The ship needs, built into its culture from launch, a genuine commitment to honesty about what the data shows. Even when the data is inconvenient. Even when the leadership would prefer it said something else. This sounds obvious. It is not obvious to implement in a human community that will face real stress across real decades. Consider what happens when disease arrives. Not a dramatic pathogen from outside. Something that was already there, dormant in someone's biology, activated by stress or radiation, or a random mutation in the confined microbial ecosystem of the ship. In a closed environment with a fixed population, a disease can spread faster than the medical team can respond. The ship has medical facilities, but not the resources of a planetary civilization. No pharmaceutical supply chain bringing new medicines. No specialist hospitals to transfer critical cases to. What the ship has is what it launched with, plus whatever it can synthesize with onboard equipment and the knowledge base the medical team carries. If the pathogen is something the medical system can handle, the outbreak is contained. People recover. Life continues. If it's something the medicine can't easily manage, people are gone. Not all at once, but steadily, over weeks or months. And the losses aren't random. Certain people are more exposed. The maintenance workers who share tools, the teachers who work in crowded classrooms, the medical staff who treat the sick. You can lose critical skills in a cluster. The 3 engineers who shared a workshop, the 2 doctors who were the only ones trained in surgical procedures. Once that knowledge is gone, it's gone. You can look it up in the documentation, but documentation is not the same as experienced hands. A disease outbreak on a generation ship is not just a medical crisis. It's a skills crisis, a morale crisis, and potentially a structural crisis, all at once. Planning for this requires more than medical supplies. It requires distributed training so that no single skill exists in only a handful of people. It requires quarantine procedures designed into the architecture so that sections of the ship can be sealed off without losing functionality. And it requires a culture that doesn't panic, that responds to crisis with the same steady competence it applies to routine maintenance. Building that culture is a slow project. It requires decades of consistent institutional messaging, of practicing for emergencies before they happen, of leadership that models calm under pressure rather than catastrophizing. You have to build it deliberately from the beginning, because in the middle of a crisis, it's too late to start. There's a particular kind of crisis that plays out in slow motion, and it doesn't involve any system failure at all. It's the problem of technological obsolescence. The ship launches with the best technology available at the time of departure. Propulsion, life support, medical equipment, computing systems. All of it state-of-the-art. But civilization on Earth doesn't stop advancing. In the decades after the ship departs, better technologies might be developed. Faster ones. A ship launched 20 years after ours might reach the destination, using technology that the founders of our ship only dreamed about, and might arrive decades ahead of us, despite having left decades later. The people on board would know this. They receive messages from Earth, arriving at the speed of light, describing new breakthroughs, new capabilities. And they realize that they're using outdated equipment. That if the mission were launched today, it would be better, faster, safer. But they're stuck with what they have. That knowledge can be demoralizing. It reinforces a feeling of having been left behind, of being the slow pioneers who gave up everything only to be overtaken by people who waited. And it raises real questions. Should Earth send a resupply mission using the faster technology to catch up? In theory, if the new propulsion is fast enough, yes. In practice, matching velocity with a ship already moving at a significant fraction of light speed is extraordinarily difficult. You'd have to accelerate to a higher velocity than the original ship, catch up over interstellar distances, decelerate to match the ship's speed, and then execute a cargo transfer in deep space. The logistics are enormous. And by the time Earth develops the capability, the ship might be so far away that it's simply not worth it. The more realistic answer is that the ship is on its own, using technology that becomes more outdated with each passing year, knowing that the universe is advancing around it in ways it can't participate in. This is not a crisis in the immediate sense. It's a psychological weight that accumulates over decades, and a practical constraint that limits the ship's ability to solve problems it wasn't originally designed to handle. The communications situation compounds this. The ship maintains contact with Earth via laser communication. Data, transmitted at the speed of light, focused into a tight beam that carries information across the growing distance between the ship and home. In the early years of the journey, the communication lag is manageable. A few light years means messages take a few years to arrive. You send a question and wait years for the answer. Not ideal, but workable. By the middle of the journey, the lag has grown to years, sometimes many years, depending on the destination. You are essentially communicating with people who live in the past. The Earth that answers your message is the Earth of years ago. The Earth of right now will not answer you for years more. This isn't just inconvenient. It gradually severs the psychological connection between the ship and the civilization that launched it. Earth becomes history. A place you receive transmissions from, a voice from the past, but not a living community you're part of. By the later generations, the transmission lag is so long that communication with Earth is essentially historical research. The ship is alone in a way that no human community has ever been alone. Not just geographically, temporally. Separated from the rest of civilization by a gap of time, not just distance. There's also the problem of what happens to knowledge over time. The ship launches with a full library. Every scientific paper, every engineering manual, every medical textbook available at the time of departure. All of it preserved in digital systems, backed up redundantly, cross-referenced and searchable. The first generation knows how to use this library because they learned in the same educational environment that produced it. The concepts are familiar. The terminology is consistent with what they were taught. The second generation learns from both the library and from their parents. Some drift begins here. The language of the documentation and the language of daily life start to diverge slightly. New terms arise for things specific to the ship. Old terms fall out of regular use. By the fifth generation, consulting a technical document from the library requires a small mental adjustment. The vocabulary isn't quite the language they speak. By the 10th generation, some documents are difficult. By the 20th, some are effectively written in a foreign language. Not in a dramatic way. Not all at once, but gradually, consistently. The living culture and the archived knowledge pull apart. And at some point, when a maintenance crew needs to consult the original design specifications for a failing component, they find documentation they can understand only partially. They make their best interpretation. They act on it. If their interpretation is right, the repair succeeds. If it's wrong, the repair fails. And the person who could have explained what the original documentation meant has been gone for 200 years. This is not a hypothetical. It's a documented pattern in any organization where technical knowledge passes through generations of practitioners without direct contact with the original developers. The knowledge degrades. Not always dramatically, but it degrades. The generation ship has to be designed to counter this, which means the educational system on board cannot simply transmit information. It has to transmit understandings. The difference between those two things is the difference between a technician who knows that if you turn valve 7 counterclockwise, the pressure drops, and an engineer who understands why the pressure drops and can therefore predict what happens when the same principle applies to a different valve in a configuration that's never been documented. Training the former is straightforward. Training the latter requires resources, time, and a culture that values deep comprehension over procedural competence. You need that culture. You cannot afford to lose it. This is why the education system on a generation ship may be the most critical system of all. Not the engines, not the reactors, not the life support, the schools, Because the engines can be understood only if there are engineers who understand them. The reactors can be maintained only if there are physicists who understand the underlying physics, not just the procedures. The life support can be managed only if there are biologists, chemists, and systems engineers who understand the science deeply enough to handle situations that no procedure was written for. Produce a generation of people who follow procedures without understanding them, and you've set a clock running. The moment the situation diverges from the expected, they're lost. Produce a generation of people who understand the science, and you've given them the ability to adapt, to improvise, to solve problems that nobody anticipated. That's the difference between a generation ship that arrives and one that doesn't. One of the strangest aspects of a multi-century journey is the relationship to time itself. Not time dilation, the relativistic effect that makes time pass more slowly for objects moving at high speeds. At 1% of light speed, relativistic effects are real but small. The crew ages at nearly the same rate as people on Earth. The strangeness is different. It's the relationship to historical time. The ship launches in a specific year. Call it a decade or two from now. The first generation on board is connected to that moment. They remember the world before departure. They have context for the decision to build and launch this ship. They understand, in a lived way, what was happening on Earth when they left. The 10th generation has no such connection. To them, the launch year is history. The way that people today relate to the founding of their country or the events of a century ago. You know about it. You've learned the story. But you weren't there. And the things that seemed urgent then, the political debates, the scientific controversies, the cultural conflicts that shaped the decisions being made, have been resolved or forgotten. They've become context rather than present reality. The 20th generation is further still. The launch year is ancient history. The founders are figures from a story, like the people who built something great and famous centuries before any living person was born. You honor them. You tell the story. But you don't think you're one of them. You think you're the inheritors of what they started, which is true. But the practical effect is that the further the ship gets from its launch date, the more the mission exists as an inherited obligation rather than a lived commitment. And inherited obligations are hard to sustain across generations if the inheritance doesn't come with enough meaning to make the cost feel worthwhile. The ship has to keep generating meaning, not just transmitting it from the past. Not just pointing to the founding documents and saying this is why, but generating it freshly in the lives of the people currently on board, in the work they do, in the community they inhabit. The meaning has to be present tense, something they experience now, not just something they've been told was important once. The communities that have sustained themselves across long timescales, across generations of people who never chose to be part of them, are the ones that found ways to make membership meaningful in the present. Not by coercion, by giving people something real to be part of. Work that matters. Community that supports. A sense of place that belongs to you, even though you didn't choose it. These things can exist on a generation ship. They have to be designed in, and they have to be maintained. That's one more job for every generation, to keep meaning alive. In a place where the stars don't move and the destination is always centuries away. There is a version of this that works. Not perfectly, but well enough. It requires some combination of technologies that are not yet available, but are not obviously impossible. Suspended animation reliable enough to keep people alive across decades. At minimum, genetic management systems capable of maintaining population health across the full journey. Automated systems sophisticated enough to handle unanticipated failures without human supervision. A governance framework that can adapt across centuries without losing the core commitments that make the mission coherent. And it requires something that cannot be engineered. A culture on board that genuinely values the mission, not as an imposed obligation, not as a rule in a document, but as something the people feel, something that shapes how they see themselves and each other and the work they do. A culture that tells the story of the journey as a story worth living inside, that believes the destination matters, not because they'll see it, but because their descendants will. That finds meaning in the passage itself, in being part of something that will outlast everyone currently alive. Cultures like this have existed. They're rare. They require careful, deliberate construction, and they require conditions that support them. You can't build a culture of collective purpose in a community where resources are desperately scarce and people are fighting for survival. You need stability. Enough food, enough space, enough predictability in daily life that people can afford to think about something beyond immediate need. The ship has to be designed from the start to provide that stability, because without it, the culture you need cannot grow. This is why the engineering and the sociology can't be separated. The physical ship determines the conditions of life on board. The conditions of life determine what kind of society can form. The society determines whether the mission succeeds. You cannot build a great ship and a dysfunctional community and expect the ship to compensate. The two have to be designed together, from the beginning, by people who understand both the physics and the psychology. That kind of integrated design is itself something we're only beginning to develop the tools for. Some researchers have proposed alternatives that sidestep the multi-generational problem entirely. Suspended animation would allow passengers to spend most of the journey unconscious. Their metabolism would be reduced to near zero. Aging would slow dramatically or stop. The crew would effectively sleep across the centuries and wake up near the destination. The appeal is obvious. You eliminate most of the social complexity of a generational voyage. You don't need to manage a society across centuries. You just need to keep the sleeping people alive. And here's the thing. The technology to do this, at least partially, is not as far away as it once seemed. Medical research into therapeutic hypothermia, deliberately reducing body temperature to slow metabolism and reduce damage during cardiac events or surgeries, has been advancing steadily. There are proposals to extend this to longer periods, using a combination of reduced temperature and chemical agents to maintain a stable, low metabolic state for months or even years. Some researchers believe that weeks-long suspended animation for humans is possible within decades. Years-long suspended animation is more speculative. Decades or centuries long is in genuinely unknown territory. The challenges are not trivial. At very low temperatures, ice crystals form inside cells and destroy them. Cryoprotective agents can prevent this, but the agents themselves are toxic at high concentrations and have to be carefully distributed through every tissue in the body. Getting the chemistry right is not simple, especially for a nervous system that has to resume function intact after centuries. That problem has not been solved. There is also the question of what keeps the ship running while everyone is unconscious. You still need systems that maintain the hull, manage the trajectory, monitor for unexpected hazards. You can automate these, but automated systems fail. And when they fail, there's no one awake to fix them. So you'd need a small crew, maybe rotating shifts, with some people awake at all times while others sleep. Or you'd need automation sophisticated enough to manage any realistic failure scenario without human intervention. Neither of these is trivial. But neither is it obviously impossible. The hybrid model, where most of the population sleeps but a rotating skeleton crew stays awake to maintain the ship, is probably the most viable near-term version of suspended animation travel. It dramatically reduces the social complexity of the voyage. A skeleton crew of perhaps a few dozen people, cycling through wakefulness in shifts of several years each, can maintain the ship without needing to sustain a full civilization in motion. They wake, they work, they hand off to the next crew, they sleep. No need for schools. No need for governance structures that span generations. No need for agricultural systems that feed thousands. Just enough people awake at any given time to keep the ship alive. The people who arrive would be the same people who launched. Older, perhaps, accounting for the years of wakefulness spread across the journey. But the same individuals, with the same memories, the same sense of connection to Earth and to the mission. This solves many of the social problems. It introduces new ones. What happens to a person who spends 50 years of wakefulness across a 300-year journey, waking for a few years at a time, sleeping away the decades in between? Their relationships with the sleeping passengers, friends and family in suspension, are frozen. They come back to the same person they left, unchanged by time, while the waking crew member has aged and changed around them. That asymmetry in lived experience is psychologically complex in ways we don't fully understand. And if the suspension technology fails while people are inside it, the consequences are catastrophic and irreversible. You are not sleeping with a safety net. You are trusting your life to a system that has to work perfectly for centuries with no possibility of external maintenance. The probability of failure per year may be small. Over 300 years, those small probabilities accumulate into something that cannot be ignored. There's another proposal that takes a completely different approach. Instead of sending living adults in suspended animation or sending a self-sustaining generational population, you send the information needed to make humans and reconstruct them at the destination. Frozen embryos, or just digital sequences of human genomes, sent aboard a small and lightweight probe. At the destination, an automated system, an artificial intelligence capable of operating independently, handles the construction of the infrastructure needed to receive new life. The embryos are gestated in artificial wombs. The children are raised, to whatever degree a machine can raise a child, until they're old enough to manage themselves. Then they build the colony. This is sometimes called embryo space colonization. It solves the mass problem. Embryos and genome sequences weigh essentially nothing compared to a crude ship. You can send multiple probes to multiple destinations simultaneously. If one fails, others may succeed. It solves the social continuity problem. There's no multi-generational community to maintain in transit. Just machines doing their job. But it introduces a problem so large, it tends to stop the conversation. You are creating children, human beings, at the destination, with no parents, no community, no culture. Raised by machines. The first generation of a new world, born into a situation that no human has ever experienced, with nothing to guide them except whatever programming the machines carry from Earth. The question of whether this is ethical is not a simple one. You could argue that those children would have lives worth living, that the alternative is never bringing them into existence at all, that their situation, however unusual, is a foundation from which they could build something real. You could also argue that creating human beings in conditions of radical isolation, with no human caregivers, no genuine community, no culture in any meaningful sense, is an act of extraordinary cruelty, regardless of the intention behind it. This debate doesn't resolve cleanly. It probably never will. What it illustrates is that every version of the generation ship idea, every proposed solution to the problem of crossing interstellar distances with human beings, eventually runs into something that isn't an engineering problem. It runs into a question about what we owe each other. What obligations the living have to people not yet born. What it means to choose something on behalf of someone who cannot choose. These are old questions. They appear in every civilization, every legal system, every family that has ever tried to build something that would outlast the people who started it. The generation ship makes them concrete and urgent in a way that nothing else does. The arrival at the destination star system doesn't happen in a moment. It happens over years. The deceleration phase of the journey is just as demanding as the acceleration phase. You can't arrive at a star system moving at 1% of light speed and simply stop. You have to decelerate. And deceleration requires the same kind of energy as acceleration, just applied in reverse. The engines fire in the forward direction. The ship slows down. Gradually, over years. During this deceleration phase, the ship's orientation changes. The thrust axis shifts. The internal gravity environment changes character as centrifugal gravity and deceleration thrust interact. People feel it, not dramatically, but perceptibly. The ship moves differently than it has for their entire lives. For the last generation of the journey, the one that will actually arrive, this is the beginning of something new. They grow up knowing they're the ones who will see it, the ones who will arrive, the ones for whom the journey ends and something else begins. That knowledge shapes them in ways their predecessors weren't shaped. Every generation before them lived in the middle, the endless middle, the journey that had no near end. This generation lives at the edge of arrival, and that proximity to destination changes the psychological landscape of the community. There's excitement, anxiety, a sense of responsibility that their predecessors could defer to future generations. Future generations have run out. They're the future generation. The weight of that is real. The other side of that weight is the question of what arrival actually means. For 40 generations, the community has been defined by the journey. The ship is home. The routines of shipboard life are normal. The agricultural cycles, the maintenance schedules, the governance processes, the social structures, all of it was designed for a community in motion. Arriving doesn't solve the problems of building a colony on a new planet. It creates them. The skills that kept the ship running for 1,000 years are not the same skills needed to establish a civilization on a new world. Agriculture in a hydroponic system and agriculture in an alien soil are related but different disciplines. Maintaining a recycled water system and finding and developing water sources on a new planet are related but different problems. The Generation Ship community arrives with extraordinary discipline, extraordinary resilience, extraordinary ability to maintain systems under pressure. These are valuable, enormously valuable. But they also arrive with 1,000 years of adaptation to a specific, controlled environment. And now, the environment is no longer controlled. It's a planet, with weather, with geology, with biology, with all the unpredictability that a real world brings. The transition will be difficult, not impossible, but the hardest adaptation the community has ever had to make. When the ship eventually arrives, wherever it's going, the moment of arrival carries its own weight. The destination star grows in the instruments. Then, in the telescope, images. Then, eventually, in the viewport. The target planet comes into range of detailed observation. Every sensor array focuses on it. The data pours in. Atmospheric composition, surface temperature, gravity, magnetic field strength, liquid water signatures, and the people on board, the 40th generation, the 50th, however many have lived and been gone since launch, they wait. The data says the planet is habitable.